So now that we talked about cloud flashes, let's talk about ground flashes. And the most common type of ground flash is the negative CG, or negative cloud to ground lightning flash. And these are formed when we get a leader, bidirectional leader, initiating between the charge regions that are closer to the ground, typically. So you have the positive leader propagating up towards the negative charge region, mid-level charge region, and this lower positive region that I explained that forms near the base of the storm acts as the other positive charge region or other charge region which the negative leader propagates towards and through. In this case, though, it extends past it, and it's primarily due to the fact that it's not as big of a charge region, that potential well is not as large, so it can continue through and past that charge region. And the ground itself is still induced in a positive way due to the dominance of this negative charge region due to its size, and so it is driven by the electric field onward towards the ground. And eventually that leader comes down and touches the ground. Here's what it looks like with a high-speed camera. This is a negative CG flash and happens to be one of the first flashes I ever captured with a high-speed camera. So very dendritic, negative leaders branch out, and then one of those branches reaches down all the way to the ground and causes that bright return stroke. And you can see that the return stroke actually starts from the ground and travels back up that channel. This is kind of a composite with just the first frame of the return stroke included. And it verifies that the return stroke itself travels upward. So let's talk about that return stroke process. Again, you have a negative leader that's coming down, and instead of just reaching down and touching the ground flatly, what happens is as you bring this excess of negative charge or negative electrons downward towards the ground, as we continue to break down the air, the electric field between the negative leader and the ground strengthens due to induced charge because the electric field is greater due to the shorter distance. And when that distance is decreased, the electric field increases, and then objects, any kind of elevated objects on the ground will also have an additional enhancement of the electric field due to their shape, and that causes an upward positive leader to reach up and make a connection with that downward propagating negative leader. So in most all cases, when the return stroke occurs, it's actually a connection between two leaders, not the negative leader with the flat ground. And we can kind of see that process as it happens. Again, inducing positive charge, positive leader reaches up, and a connection is eventually made. You can see that quite clearly here on this high-speed video that I captured in Rapid City of a TV tower. And again, because of the shape of the tower, the field is enhanced greatly due to the elevated narrowness of the tower. And because of that, the leader was able to form much earlier in response to the negative leader coming down from above. So this is a negative leader, this is a positive leader. And this is how lightning attaches. There's a bright return stroke, and then it decays. And notice as it decays, there's a little bit of dimming right at the attachment point. So if we think about that, when the negative leader is coming down and positive leader is coming up, what actually happens when those two leaders touch and meet? Well, essentially, what you get is a intense, rapid acceleration of the breakdown process, an intense acceleration of the electrons, intense brightening due to the increase in thermal energy that's being generated and released. And so you get this bright return stroke as a result. And it's incredibly bright, it's incredibly fast propagating, and by propagating, it's propagating in a zone where the connection is made, and that increase in acceleration, increase in brightening, and heating goes in two directions. So they connect here, and then that zone of increasing acceleration and brightening travels back down that channel, that upper positive connecting leader, to the ground, while a zone of acceleration of the electrons and brightening continues upward at the same time. Now, this just shows that this is red because the electrons are moving downward, and that they're moving away from the tip of the return stroke process. And the acceleration is indicated by the length of the arrow. So you had the acceleration of the electrons at the leaders coming down, connection is made, and suddenly there's this very intense increase in acceleration, more kinetic energy, more thermalization going in both directions, but all the net direction of all the electrons is downward, still downward. And then when that zone of acceleration again touches the ground, you'll get an even further increase in the acceleration because now you're connected to the ground. Essentially, it's a conductor, and the resistance has dropped even further because you're touching the ground, and you get a much higher intensification of the acceleration, thermalization, brightness, and that's the return stroke. So let's take a look at that. There's the connection, bidirectional growth, and then enhancement again once that reaches the ground. All a matter of increasing acceleration due to decreased resistivity from the return stroke itself. So the return stroke is the bright thing that we see when we're looking visually at a storm and we see it connect to the ground, that bright flash. It used to be said that the step leader from the cloud, and I was taught this in school, step leader in the cloud is invisible, you can't see it, and that all you see is the return stroke. Well, if that was the case, we would not see any cloud flashes because they're step leaders, they're negative leaders, positive leaders. We wouldn't see spider lightning, we wouldn't see any of the lightning that it generates. But we were taught that that's invisible, and that's not true. All leaders are visible. The return stroke is much brighter than the leader itself, which is true, but we can see the leaders. We can see spider lightning. We can see cloud flashes in which the leader extends out. The whole reason the cloud is flashing when there's a cloud flash inside and we can't actually see the leaders is due to the brightness of the leader, which we would be able to see. So I want to talk a little more in detail about the leader channel itself, both during the leader phase and the return stroke phase. And it actually is composed of a relatively narrow core, around 2 centimeters. And this is the hot, intense portion of the leader channel, the plasma. And this is where the temperatures will reach up to 30,000 degrees Celsius during the return stroke. It's a very high current flow pathway, but it only stores about less than 1% of the actual charge on the leader as the leader is growing and propagating. Outside of there's a sheath, and the sheath is composed of an inner and outer portion, and that because we see a transition as the electric field decays from the inner core. There's very intense electric field generated from in this inner core, and that electric field goes out radially, and that decays, and that causes a differentiation of the sheath that surrounds the core. And the inner portion extends from 3 to 8 centimeters out from the center, and it is undergoing ionization, but it's a cooler ionization, the corona in the 2 to 10,000 C range. And so we have the ionization going on due to the electric field intensity, but it's not as hot. And this stores about 10% of the total charge on the leader in this zone. And when there's a return stroke, this charge collapses or moves inward towards that core. And in the core, we get these longitudinal current flow, but in the sheath during the return stroke, we get a lateral current flow, or radial current flow that moves inward towards that core. And outside of that, you get cooler, less ionization as the electric field again decays, and so it's an area, the outer core, that extends from 8 centimeters out to half a meter, has most of the charge residing in it. About 90% of the charge is located in this outer corona sheath. And again, when there is a return stroke, there's rapid movement of the charge stored on that sheath inward towards the core itself. And so the more detailed dynamics of the leader shape, size, dimension, and properties is much more complex than just a simple uniform leader as it's propagating. And the other point I want to make regarding this is that when there is a lightning flash, an individual electron doesn't travel very far. It's not like charge that's up in the cloud and this piece of charge travels all the way to the ground and goes in the ground during this lightning flash. That's not how it happens. The charge that's on hydrometeors is fixed and only travels with the speed of the hydrometeor. The charge that's created or from the neutral air, as neutral air is ionized and you have electrons, positive ions, negative ions, they move a relatively short distance over the course of the flash, and then the flash stops, they stop, and then they recombine. So we're really looking at a fundamental shift of charge during a lightning flash along that entire leader network pathway. And this is on the order of just centimeters. And you can think of it as you have neutral air, you ionize it, you have if you focus just on the electrons, they shift towards the area that has a deficit of electrons, or the positive charge region. They shift along the entire leader path as this breakdown occurs, and they move under the influence of the electric field, and then the flash is over. So there's a fundamental shift of electrons towards the positive charge region and away from the negative charge region, and that's how charge is moved. It's essentially created from neutralized air, and then shifts, and then stops, and then recombines. So it's an important point, I think, that when you're visualizing lightning, it's not like one piece of charge way up in the sky travels all the way to the ground. So after the return stroke, what we want to look at is the fact that you essentially had this return stroke and you had this acceleration, intensified acceleration, thermalization, and brightening that goes back up the pathway all the way through the leader network and to the extremities of the previous existing leader network. And you need to remember that this was originally positive leader propagating into the negative charge region. So now essentially this whole thing has become positive because it can continue to grow in this charge region after the return stroke, and it's going to grow as a positive leader. It's going to keep breaking down in a positive breakdown way. And so a post-return stroke channel or post-negative CG return stroke channel is a positive leader that continues to grow if it sustains itself. So let's talk about some flash components of a negative CG flash. We talked about leader initiation and development and the return stroke. Well, there's things that can happen after. It could just die out, or we could see what is called continuing current, and that means that the upper portion of the flash, the positive leader, continues to grow, and if that's the case, the whole thing remains luminous, and that's called continuing current. Or the flash may decay itself, the whole channel to ground even, and then we'll see redevelopment in the upper portion of the flash, and the leader comes down and causes a subsequent return stroke. And that's very common. That's the flickering. We see subsequent leader return strokes that go back up, and that multiplicity is due to recoil leader development. Or we can just see that the flash is connected, it's still bright, it's still luminous, and by connected I mean the upper leader is growing. It's not connected to anything because it can't connect to anything in the cloud. The cloud charge is not a battery that you connect to and then run current through. It's charge that's on hydrometeors that are fixed. They don't move other than the motion within the storm. So that charge can't just suddenly move or be like a straw as far as draining down. It's the leader moving through the charge. And so if that leader continues to grow, and then there's subsequent recoil leaders on various branches, we call those M components, and we'll show those here in a minute. So let's look at these components. In the first case, we'll just see the simple decay of the leader after the return stroke. I've simplified the charge regions into negative charge layer, positive charge layer, and we'll see that the positive leader goes up and the negative leader comes down. The return stroke rapidly goes up, intensifies the brightness, and then the whole thing decays. In the case of continuing current, what we're going to see is that some leader activity post-return stroke is going to keep propagating. So you get this development, the negative leader coming down, positive leader going up, the return stroke, which goes through the channels, some of those of which might decay, but if it keeps growing after that, it will illuminate the whole channel as current flows, in this case electrons coming downward. In essence, you're transferring negative charge to ground. That's why it's called a negative CG flash. If that happens and those leaders continue to grow, that's called continuing current because the luminosity continues due to this leader growth. In the case of a multi-stroke, which the channel has you have a return stroke, everything decays, you don't see any luminosity to the ground any longer, but then there's this subsequent return stroke. The leader comes down, causes another return stroke. That is caused by recoil leader. That becomes what we call a dart leader and touches the ground. Again, it grows, it can decay, and when everything decays here, we can get a recoil leader that forms, and the negative end comes all the way back to the ground and causes another return stroke. And again, if that leader comes all the way to the ground, that's considered to be a dart leader. And that's how we get multiplicity in negative CG flashes. Now, if a portion of the leader network continues to grow and we still have the continuing current, so that we have a luminous channel to ground, still luminous, and we see a sudden brightening in that channel, what's going on there is that we have a decayed branch somewhere that has developed a recoil leader, and that recoil leader has connected to the luminous channel and caused it to brighten up. And these are called M components. Return stroke, continued growth, continuing current. This one decays and develops a recoil later, causes some brightening. And we'll go back and look a little more closely at that. So we have the return stroke, continuing current, decay by that branch, but then we get a recoil leader along that branch, and it connects to the main channel and causes that main channel to become more luminous. And that's an M component. So let's look at a negative CG flash captured with high-speed camera. And this flash contains all the components that I talked about, as well as one that I've only seen one other time before. And this flash was captured near Rapid City. This was at 7,207 images per second. And for reference, this vehicle is probably going around 60 miles per hour. And what we're going to see is the step leader come down and cause a return stroke here. Here's some branches. These do not reach the ground. The first return stroke will decay rather quickly. And then what is unique, and I've only captured one at a time, is this leader come down, a new step leader from a different spot come down, and then jump over and then accelerate as a dart leader after connecting to the still somewhat conductive channel. Even though you can't see it visually, it's still residual conductivity. Accelerate down as a dart leader and cause a subsequent return stroke. And then after that, we'll see multiple dart leader return stroke sequences coming down both pathways. We'll see recoil leaders where the negative end extends down these branches, but then just decay. They don't extend the channels any further, nor do they reach the ground. And so we'll see those processes, and then it'll establish continuing current where this main channel remains luminous. And that's due to, again, to the upper portion positive leader activity that's growing through the negative charge region, maintaining that current flow through the entire channel. And during that process, you'll see these rapid brightenings of the main channel. Even though it's luminous, it'll brighten even further very rapidly. That's the M components that we talked about, where recoil leaders and decayed branches in the upper portion of the flash connect to the main channel, causing an intensification. And you then might see some variability of the main channel, and that's as the upper portion of the leader network, the positive leader, is growing and encountering other areas of more dense charge, and therefore increased electric field between the leader and the cloud charge, and therefore grow more rapidly, more intensely, and cause the entire channel to become more luminous, but not as rapidly as we see with the M component brightening, which is due to recoil leader activity. So step leader, turn stroke, decay, couple recoil leaders along the branches. Now we see this new step leader initiate separate, but jump over to the main channel and cause another return stroke. And now we see a series of dart leader return strokes along both channel paths. Some of them don't reach all the way to the ground. Some do. So now we've entered the continuing current phase, and you see this rapid brightening of a luminous channel. Again, that's due to the recoil leaders up in the decayed branches connecting with that main channel as it's continuing to grow. And the continuing current, this is what causes heating on the ground where the connection point is, because it's sustained over a longer period of time, and that's what can cause fires. And flashes with continuing current are more likely to start fires due to that sustained current and more heating. Again, this vehicle is traveling about 60 miles per hour. And this whole sequence that I'm showing you, all that's occurred here, and it's still a little ways to go, is 0.6 seconds. There's a wiper coming into view. And we'll see one last rebrightening after the wiper gets out of the way. So a lot can happen in a very short period of time in regards to lightning. In fact, when I'm out capturing it, I'll see the flash. Like when I saw this flash, it flickered. There was a lot of other flash activity. It lasted fairly long, and that was due to the continuing current. But that's all I saw. I just saw there's a flash. It flickered, and it lasted about a half second or so. And when I captured that with a high-speed camera, I feel like I caught the title of a novel and a multi-stroke flash. But then when I get and start looking at the high-speed camera imagery and looking at it frame by frame, it turns into a novel with many different chapters, plot turns, twists, all kinds of different things going on. So that's how I describe what it's like to film this with the high-speed camera. Let's look at another one in which we can actually see some of the recoil leader activity up in the cloud that causes subsequent return strokes. So here's the negative end, positive end with some branches, but we'll actually see recoil leaders form and cause dart leader return stroke sequences. So these are recoil leaders occurring before the return stroke. Here's the negative leader coming down. Turn stroke, and some of these will transition to dart leaders and reach all the way to the ground. M component, another one. More. So in this case, we can verify that those M component brightening are due to recoil leader activity occurring in the upper portion of the flash. So now let's look at a unique type of negative CG flash, but this is called a bolt from the blue, and this occurs from the upper portion of the thunderstorm. And these are quite spectacular in that they extend far out from the updraft core and extend way away from the storm itself and the area where precipitation might be happening. And these are very dangerous because some people equate I can only be harmed by lightning if it's raining or the storm's right over me, but that's not true. And this is how bolt from the blue flashes occur. In the case of a negative bolt from the blue, which is actually most common, you get a development between the mid-level negative charge region and upper positive charge region. And you'll get the negative leader grow up towards and into the upper positive charge region, the positive leader into the negative charge region. But whether there's kind of erosion or mixing that decreases the charge density or charge amount and size of that region, a negative leader extends out from that charge region and exits the storm and continues onward down outside the updraft base all the way to the ground before touching the ground outside the storm. And it's still kind of unclear exactly what's driving this, other than there's likely a deficit of positive charge or a smaller well for that negative leader activity to propagate through. And then also why is it turned towards the ground? Well, likely because there's some positive screening charge along the negative main charge region that might cause it to curve that way and induce positive charge on the ground. Now, as this leader approaches, it's definitely going to induce more positive charge on the ground to make the connection. But most of the bolt from the blue lightning flashes that you see are negative CG flashes. They originate in the upper positive charge region, but it's because of the negative leader that propagates into that region and outside of it all the way to the ground. Here's an example that I captured in Australia, and you can see how this leader comes out of the cloud, and the shape of it shows that it's clearly, to me, it's clearly a negative leader based on its appearance. So let's look at this at high speed. This is in Brazil, and these usually happen with tropical type thunderstorms, where you get this high cape, intense buildup, but not a lot of wind shear that causes them to turn into supercells per se. But it's more just a main updraft. There could be some shear and some tilt, but it tends to be in the early phase of the storm, and it happens. You typically might see a few cloud flashes, and then an attempt of a leader coming outside the storm, and then another attempt, and then finally a one that actually travels all the way to the ground. And one person that's recorded a lot of these is Mike O'Neill in Australia and Darwin. He's captured this, and he's observed this pretty much the entire time that he's storm chased for many years. And in many cases, he can just sit there and say, yeah, that's going to produce a bolt from the blue as it's growing, and sure enough, you get that exact thing to occur. And these typically occur before we get any really well-established precipitation. In this case, if we do have precipitation occurring, but definitely before you start seeing negative CG channels that come to ground in the rain core area. So let's look at this process. So that's definitely a negative leader, and the steps are quite long into the higher altitude rarefied air, which was observed. Harold Edens did a study on this and noticed that the stepping length was much longer in the higher altitudes, and then shortened up as it got closer to the ground. Never seen a more frequent, shorter stepping. And connection. And sometimes you will see subsequent return strokes, recoil leader, dart leader, return stroke sequences with these. Sometimes you do not. Let's look at another one, same storm a little bit later. So I remember in school I was taught that anytime you see a flash from the upper part of the storm, that is a positive flash, because that's where the positive charge region is. And that's not true based on the research and the evidence by the high-speed cameras and all the work done with the lightning mapping array, and that was pointed out by Harold Edens and then Paul Kreibel in their paper in 2008 that clearly showed the bidirectional and the nature of these types of flashes. Because lightning isn't just a positive charge region that spits positive charge down as a positive leader that causes a return stroke. That's how it used to be explained, but that's just not true. This bipolar bipolar, bidirectional process is what occurs, and we clearly can show that that is true, and that is the case. So do you ever get positive cloud-to-ground flashes that are from the bolt from the blue variety? Well, I personally have only seen negative from the backside of the storm, like I just showed, but there's been times that you see intense positive activity from the vault region of a thunderstorm. This is the vault region where you have the inflow. Here's the anvil overhang in the area. And what's occurring here is the fact that you have a positive charge region in the upper portion. And again, you need two charge regions in order to initiate a bipolar leader. And so you get the screening layers that develop on the cloud boundaries. In the case of the vault, it's a negative screening layer, both at the base and on the top of the storm, designated by this. And you can get a negative leader that propagates into that positive charge region, and a positive end of that leader propagate out and down from the vault region and continue past that screening layer and continue on to the induced negative charge on the ground, and resulting in a positive cloud to ground flash. And therefore the return stroke is negative, and that it propagates up into the positive charge region and is essentially a negative leader if it continues after that return stroke. But the return stroke is a process in which negative charge is brought towards that direction due to the electron flow direction. So, positive cloud to ground flashes can also occur if you have an inverted storm in which the mid layer is positively charged, the lower, smaller region is negatively charged, and again you get this development between the two charge regions. But in this case, with an inverted storm, you get negative leader going up in the positive charge, positive leader down towards the ground, and continuing onto the negatively induced charge on the ground and causing a return stroke, but in opposite polarity than the negative CG. So in this case, with the positive CG, essentially negative charge is raised upward. With a negative CG, and that's why it's called negative CG, is that negative charge is effectively lowered to ground. Electrons are transferred to ground. With a positive CG, electrons are raised from the ground, going upward away from the ground. So let's talk more about the positive CG flash components and compare them to what we see with negative CG flashes. Again, you have the leader initiation and development. You can have the return stroke. That channel can just decay. But often what we see with positive CGs is continuing current. And again, after the return stroke, you could be left with a negative leader that's continuing to grow. And if so, that will keep the whole channel pathway luminous and conducting current. And that's the negative end. It's now all a negative leader growing, and electrons are accelerating in the upward direction. And it could decay, and then you can get redevelopment on negative leader branches and pathways, which could lead to a dart leader return stroke sequence like a negative CG, but it's quite rare to see this. And we need to understand why that is, because negative leaders don't produce recoil leaders like positive leaders do. There's some evidence that they can produce recoil leader activity, and it's still kind of debated how clear that is or whether or not it's a response to something else. But that redevelopment that can occur on decayed negative branches that I've already showed you that takes place is what initiates that dart leader return stroke sequence, and it's much more rare. I've only captured a handful of multi-stroke positive CG flashes myself. What you can get is M component activity, and again, then that's due to the negative leader growth, but it's, again, redevelopment on negative leader branches. So let's look at that. Here we got positive leader coming down, so it's a positive CG flash. We get the return stroke. And if it continues and the negative leader ends continues, there's your continuing current. If that decays, you might get redevelopment on one of the branches, which is what we'll show next. But most often, this is what happens. It just grows, and quite frequently, there's an efficiency of negative leader growth that tends to be greater than positive leader growth. So very frequently, we see continuing current with positive CGs much more often than negative CGs. And let's look at one of these. So here is a positive CG from the vault region, like I demonstrated. And what you're going to notice about this is how it is widely branched, fairly visible, lots of recoil leader activities, and then transitions to a bright, non-branched luminous leader before making the return stroke. This is 7,207 images per second. I did an image stack on the right so you can see the cumulative luminosity. So lots of recoil leader, very faint branches, faint channel, but then it's going to brighten up intensely as it reaches the ground, towards the ground. And that's just prior to the return stroke. Again, here is the complete opposite in the sense it's not branched. It's mainly a single luminous channel, attempts to branch. This one I showed earlier at 100,000 images per second. This is now at 10,000 images per second, same flash, wider angle. So meandering, luminous positive leader. And return stroke. So we can actually see sometimes the upper portion of a flash following the return stroke, and we can actually show that in fact that it behaves as essentially an upward negative leader following the return stroke of a positive CG flash. In this case, we're going to see positive leader come down, make a return stroke. We're going to see some of the in-cloud brightening due to the negative leader activity associated with that. And then post-return stroke, we're going to definitely see negative leaders that are attached to this. So essentially, this is a big upward growing negative leader following the return stroke. I call this post-return stroke negative leader extension. There's positive leaders on the left, in-cloud brightening due to the negative leaders. Here they are visible. And we'll see the return stroke is going to travel along that pathway that was established and then continue to grow. And as those leaders grow, you can see the channel remains luminous all the way to the ground. That's continuing current. So now we're going to talk about positive cloud-to-ground flashes that are multi-stroke. And again, these do not occur very often based on our observations, and the literature supports that. But why is that? Why don't we see more of them, more multi-stroke positive CG? We see positive multi-stroke with different termination points, different points on the ground due to branches and subsequent branches reaching the ground, but those aren't in the same channel. due to a dart leader return stroke sequence like we see so commonly with the negative CGs. Well, the one idea is that you do get a negative branch that decays, and like we showed, that redevelopment occurs along a branch point or at the branch point, with the negative portion continuing on out the branch. Positive portion will continue downward as a dart leader, and if it reaches all the way to the ground, that would be a subsequent return stroke. And we do have, like I said, a few examples of these, but we don't necessarily have the upper portion. So here's a positive leader that's coming down. Connection dies out, and a subsequent dart leader return stroke. So clearly a multi-stroke, same channel, positive CG flash. Another example. In this case, we can see some brightening occurring before the subsequent. So clearly something up in here occurred, so we think it's that redevelopment on a decayed negative branch, and the positive end reached all the way to the ground. So another possible mechanism is that instead of redevelopment on a decayed negative leader branch, we actually get a brand new negative step leader branch that forms somewhere along the channel. And this is a brand new, so it's stepping in virgin air. And again, due to the bipolar nature of leader development, we get the positive end coming back to ground. And this is an example of that mechanism. This was captured at 1500 frames per second. And you'll see as it develops, new development causes the subsequent stroke in the same channel. So there's the first one. We only see the positive leader during the first return stroke. But following the return stroke and decay, we see negative leader branch form from the channel. Now this was another return stroke, same channel, but it must have come from up in the cloud. The decayed branch up in the cloud. But here we get a visible branch. And another return stroke sequence. And this one illuminates this new branch following that return stroke. So in this case, we had 3 same channel return strokes, the initial and 2 subsequent. And the first 2 seem to originate up in the cloud, whereas the third one seemed to do to the activity of the newly formed branch that was visible, that we actually see, and then that return stroke actually traveled up and out that new branch. So now let's transition to what we call bipolar ground flashes. And in this case, we have a positive CG flash where we have the return stroke, but then subsequent to that, along the same channel, we experience a negative CG flash or return stroke. So the first one is a positive CG where negative charge is essentially lifted from the ground, or you could say equally positive charge transferred to ground, hence the positive CG. But then subsequently, negative charge is lowered to ground as a negative CG return stroke. How does this happen? Well, what we've shown with the high-speed video is that you can get positive branches, initial positive branches that decay and then form a recoil leader along their path and cause a subsequent return stroke of opposite polarity. And then they can cause more subsequent return strokes, negative polarity return strokes. So let's look at that again. So we get positive leader coming down. Notice that this branch has started to decay. It does not participate in the return stroke. The return stroke goes up, travels through the leader network, and the whole flash now is decaying. But we get a recoil leader in this decayed branch that occurred during initial development, downward development of the positive leader portion of the network. This recoil leader then would have a negative component, and instead of going up towards the positive charge in the upper portion of the cloud, for some reason it rejoins this decayed but it's probably still conductive channel pathway and turns the corner and actually goes down instead of up, and continues all the way to ground, causing a negative CG return stroke. And a lot of times when this happens, we see those decay and subsequent negative CG return strokes along that same pathway. So they tend to be multiplicity in the negative sense after that polarity shift. And this is the example that we used in our paper where we described this process. You can see the positive leader coming to ground with recoil leader activity, return stroke of nearly 40 kiloamps. But then you start seeing some recoil leader activity off to the side, and one of these causes the negative end to go downward, connect to ground, and that registered as a negative CG. And then it kept producing more negative CGs after that. Quite a bit more. So now that we understand ground flashes, we're next going to take a look at my favorite type of storms, and that is horizontally extensive storms and horizontally extensive lightning flashes. And these are related to storms that grow upscale into mesoscale convective systems and the lightning they produce.